calculate what is the work done by the gas. Okay, so remember what I said earlier, the work done is the area under the graph. So work is equal to, well, we're going to take the 50,000. Let's keep this here and not erase that. So P times delta V, the area under the graph. So 50,407.78 times the difference of that, 1.2 minus 0.5. So 50,407.78 times 1.2 minus 0.5, 0.7. So the work done by the gas is going to be 35,285.45 joules. So about 35 kilojoules, right? The gas does 35 kilojoules of work. And in regular joules, you have to have all these other numbers, 285.45 joules. Okay? Now we're going to start analyzing this one here. Delta E of gas, work by gas, heat into gas. So we know work by done gas. How do we calculate delta E of gas? Right? So how do we get the delta E of the gas? I put over here the temperature final in Kelvin. Okay, so we know the energy of the gas, okay, is going to be 3/2 kT per particle. We talked about that before. And if I have an n number of particles, we can say the energy is equal to 3/2 nkt. We're assuming here that the kinetic energy of the particles and the total energy of the particles are the same. So we're assuming that the gas is a monatomic gas, that it doesn't have internal energy due to its potential energy. So the kinetic energy of a gas, when it's equal to the total energy, and the kinetic energy is equal to 3/2 nkt, that's also going to be equal to the total energy of the gas, if there aren't any other sources of energy due to diatomic molecules or higher order level of molecules. Okay, so if the total energy is 3/2 nkt, that's also equal to 3/2 nRT. Okay, so the delta E is going to equal 3/2 nR delta T. Okay, so all I need to do is to find the change in internal energy of the gas is the 3/2 number of moles, the gas constant, change in its temperature, and I know its temperature final over here. So I'm going to do delta E is equal to 3/2 the number of moles, which is 8.314. The change in temperature that we need is equal to the final temperature, 727.56, minus the original temperature, 303.15. I could also subtract the temperatures in their Celsius version, because the change in temperature in Celsius is the same as the change in temperature in Kelvin. Okay, but since I have the Kelvin written here, I'm just going to use the regular Kelvin. I mean, I could just use the Celsius also. Okay, so now I have here 1.5. The delta E is going to equal 52,928.17 joules. Okay. Okay, so basically what's happening is that the gas is doing 35 kilojoules of work. The internal energy of the gas is increasing by about 53 kilojoules, right? And so how much heat went into the gas? In other words, how is the gas being enabled to do work and also change its internal energy? Okay, a lot of heat must be coming in, right? So you got to add these two. Okay, so Q into the gas, we just basically have to add this to this. Q into gas is going to equal 35 plus that. So we basically have this one, 52,928. We got to add that to 35,285.45. 88,213.62 joules. Okay? 88,000 joules of heat. If I want to just simplify that, just in terms of kilojoules, I would say, okay, you have 88.2 kilojoules of heat are coming in. Okay? The gas is doing 35.3 kilojoules of work. And its internal energy is increasing by 52.9 kilojoules. Without all those other digits, right? Now let's answer the second scenario. In the second scenario, we're going from its initial state to its final state, but instead it's telling us how much heat is coming in. 80 kilojoules of heat. Well, what is that? That's a little bit less than this, right? Right now it's 88 kilojoules of heat are coming in. This one is saying not that much heat is coming in, only 80 kilojoules. So it's stipulating that condition, less heat is coming in. And it's also stipulating what its final temperature is. It's 400 Celsius. Instead of 454 Celsius, it's not heating up as much, right? So what's going to happen here? What's happening to this gas? Not as much heat is coming in, its final temperature is not as hot. So what do we have to do? Well, we have to find the final pressure, right? Since this is not going to be isobaric, we have P1 V1 over T1 is equal to P2 V2 over T2, right? We know the initial pressure is equal to 50,407.78 pascals. The original volume is equal to 0.5. The original temperature is equal to 30 Celsius, so that's 303.15. The final pressure we don't know, right? The final volume is equal to 1.2. And the final temperature is going to equal what? Well, the problem stipulates that 400 Celsius, 400 plus 273, it's going to be 673.15. So from this, we can actually calculate the final pressure. Okay? So it's going to be the product of 50,000, 407.78 is equal to 46,638.08 pascals. So the final pressure has dropped. Ah, interesting. So because not as much heat was coming in as in the first scenario, the gas did work, but not as much work. It didn't heat up as much, okay? And its pressure actually dropped a little bit. So the PV diagram of that one looks like what? It looks like this now. It looks like here, goes down, and the final pressure is, what was it, 46 kilopascals, right? So the pressure has dropped, 46 kilopascal. So we would anticipate, therefore, the area under that graph is a little bit less. The gas does less work. So how could we find the work done by the gas? We can't do PV. We can't even integrate this. So because we don't know the path that it took. But we do have information as to the change in its internal energy, right? Well, notice, it told us how much heat came in, 80,000, right? So if we know what this is 80,000, how do we find the change in its internal energy? Okay, let's come here and let's find the delta E. Delta E is equal to 3 halves NR delta T. Number of moles 10, 8.314. Delta T. Remember delta T, I could do it in Celsius. So let's not even worry about Kelvin now. its final temperature 400 Celsius, subtract its original temperature, which is 30 Celsius. Okay? So let's calculate that. 1.5 times 46,142.7 joules. Okay? Before, the change in its internal energy was more, because more heat was coming in, it had gotten hotter, it was 52,000, now it's only 46,000, right? So now we know this, the problem already told us this, we can find the work without having to do any integration, right? So this one, just subtract this minus this, so what do we get here?